I have worked on a few topics, but my current focus is on dynamic treatment regimes. So I started working on this area during my postdoc around 2020. The project I am going to talk about today has been funded by National Science Foundation, and my research is also partially funded by the Career Initiation Fellowship of TAMIT. So I am looking for graduate students to work with me on this project. And so I am going to keep this talk at a high level. So I do not plan to get into much details of the topics. But for that, you might have unclarity about some stuff. So if it feels like you can't understand something, please feel free to stop me during the talk. I'll be happy to answer your doubts. Okay. So let's begin. Oops, why is not okay. So before I start getting into the depth of the topic, I just want to state what is the broad goal of this area called dynamic treatment regimes. So chronic diseases demand ongoing treatments. The question is, can we apply reinforcement learning-based techniques for optimal patient-specific and data-driven treatment policy? So now here the word patient-specific means we are looking for those treatment assignments or those type of treatment policies that will tailor themselves towards the specific need and the specific history of the patient, right? So we are not looking for one-size-fits-all strategy. So now this question is an offline reinforcement learning question. For those of you who are not familiar with the term offline reinforcement learning, so this is a sub-area of the bigger field of reinforcement learning. But I want to be very clear as to where this area stands. So although the problem is an offline reinforcement learning problem, there are some assumptions that traditional reinforcement learning made that are not suitable for the medical setting. And so although we'll be using ideas from offline reinforcement learning, the main tools that we'll be using comes from an area of statistics called individualized treatment regimes or ITR, which is a part of the bigger field of causal inference. And also my research heavily relies on non-parametric statistics. So as an area, dynamic treatment regimes actually took off in say around 2003. And it gained momentum in the last 2 decades. So here is an outline of the talk. So I'll start with an example because it will help me motivate the idea behind dynamic treatment regimes. And it will also help me to lay out the mathematical formulation of the talk. And next, I will formulate the problem I am trying to solve. I will give you a little bit of background and also I'll explain a little bit about the existing methods. Next, I'll turn to the proposed methods, but I am going to reserve rest of the talk for the open questions. Okay, so there is the plan. So let's begin. So for those of you who have been in the frontier class last week, so maybe the first 10 of the slides, you will see the same slides, but after that, you will start seeing new things. So believe me. Okay. So sepsis is a situation of the body when body's response to infection injures its own tissues and organs. And the treatment of sepsis is both expensive and challenging. So one popular treatment for sepsis is IV fluid administration. For septic patients, sometimes they need to be administered IV fluid at each hour. Now the question of whether to give a patient IV fluid in each hour or not give, that is an important question. Because if the patient does not get IV fluid when he needs, he might die. But if he gets a lot of IV fluid, since he already has sepsis and he already has weak heart, fluid overload can also cause damage. So therefore, our broad goal is to find a good quality policy for learning what should be the best strategy for IV fluid administration. So I will now concretize this idea using a particular example. So this example is from Beth Israel Hospital in Boston. So the observation starts at hour 0 when a patient is admitted to ICU. And this is also the beginning of what I will call the first stage. So in the first stage, I also observed some baseline covariates. So these covariates will relate to the heart, the kidney, lungs, and blood. So these organs are all related to sepsis. Next, the doctors will give some treatment. So in our case, I am considering the IV fluid treatment, and I will consider 4 levels of IV fluid. The first level is no fluid at all. The second one is I give low level of IV fluid. The third is medium level, and the fourth is going to be high level of IV fluid. Next, we will observe some outcomes. So the outcome is going to be a measurement. So that will tell us how good was the treatment on the patient. So there are many ways of considering an outcome like that. But for this example, I am going to use inverse lactic acid level. Now, why I am using the inverse of lactic acid level? So if the lactic acid level drops, then that means the treatment is working. So if I use the inverse, then it will mean if the inverse increases, that indicates the treatment is working, okay? So we curated it this way so that higher values of outcome will be preferable. So after that, stage 2 begins, and in the beginning of stage 2, we again observe some covariates. In this example, I will be using the same set of covariates in stage 2, but in other examples, the covariate sets in stage 1 and stage 2 can differ. After that, we will observe some treatment followed by some outcome. Now, this thing can go on for stage 3, 4 until discharge. For sake of simplicity, suppose I have a group of N patients, and for all of them, I observe total K many stages. So then what I have just described is an K-stage dynamic treatment regime setting. And our goal is to find the best sequence of treatments, which I will also collectively call a policy. Now, what makes a treatment policy or a sequence of treatments good? So treatment is good if these outcomes are large. But now I have K many outcomes. So I need a way to summarize all these K many outcomes. And I'll be using the sum as a summary measure. And so I'll say a policy is good if the sum of the outcomes is large. And I will call an policy to be optimal if that summarizes, if that maximizes the sum of the outcomes. Now, I will make this definition of optimal policy much more clear and precise in my future slides. But for the time being, if you want, you can also go for another summary measure. You can consider weighted sum, or in reinforcement learning, people also use something called discounted sum. But in this talk, I am not getting into that complications, and we are just going to work with this plain sum of the, yes, go ahead.
K is not fixed, right?
No, A is not fixed. So,
maximizing K can also relate to like maximizing Y. So this kind of maximizing is not optimal.
Yes, so I get your confusion because I am not clearly defining this pi star. So when I'll define pi star in a few future slides, then it will be much clear like what I am maximizing over. Okay. So the setting that I have just described is actually an offline reinforcement learning setting. So in the language of offline reinforcement learning, the baseline covariates and all like the covariates are known as states because these covariates describe the state of the patient in each stage. The treatment is called action that is taken on the patient after observing their state. And then the outcomes are called instantaneous rewards. And the number of stages K in the language of reinforcement learning will be called the horizon of the problem. Yes. Check this. Go ahead. Okay. And why do I use the word offline there? So although this is a reinforcement learning problem, I need to learn the optimal policy based on already available patient data. I do not get to make any real-time interactions with the environment. to make any action on the patient. So since it is based on already available data, it is called offline. And this setting has some difference with the most traditional reinforcement learning settings. In traditional reinforcement learning settings, they make two assumptions. Since I am not going to make these assumptions, I will not get into much details, but I just want to say in some quick words like what they basically mean. So reinforcement learning generally assume this Markov decision process assumption. So this means at any stage, the dynamics of the whole stage is captured only by the state. We do not make this assumption because it's not realistic for the medical setting. And also another assumption generally made in traditional reinforcement learning literature is a homogeneity assumption. That means the joint distribution of the state, action, reward, they don't vary across the stages, but we also do not make this assumption. So we allow them to have like any distribution they want. So at least they do not need to be same. And since this setting differs from the traditional reinforcement learning, so now recently this setting like dynamic treatment regime setting is, it has a new name. So it is being called the full reinforcement learning. Okay. So now to follow the rest of this talk, you do not need to have like any background on reinforcement learning. Okay. So now I will go to, probably you have guessed that the goal of this talk is going to revolve around estimating this optimal policy. So I will clearly now define the optimal policy, and I hope that it is going to clear your doubt. But before defining the optimal policy, I need to define some notations. And these notations are going to be very important. So I'll define two notations, and they are going to be very important for understanding the rest of the talk. So the first notation I am going to define is that of history. So the history has the same meaning as medical history. So the first stage history H1 is going to be everything that we observe before the first stage treatment assignment A1. The second stage history H2 is going to be everything that we observe before the second stage treatment assignment A2. So before the second stage treatment assignment A2, we see S1, A1, Y1, and S2. So H2 is going to be a vector of these four elements. And in general, for any stage K, the K stage history is going to be the vector of all the elements. So they can also be like vectors. So I am saying vector of elements, not vector of random variables, that I observed before the K stage treatment A. So now why is history defined in this way? So think about this. When you go to a doctor and when they give you a treatment, they are going to look at everything that is available to them prior to giving the treatment, right? So that means when the doctor is going to give the case test treatment, they have like all the thing available before the case test treatment up to Y, K minus 1. So they are going to look at all these elements to make a treatment decision. So all this that is trailing behind, so I'll call them the history. So the next important notion for us is going to be the treatment policy. So at stage 1, doctor looks at the first stage history H1, and at this stage, they only have the baseline covariates. That is what H1 is. Now looking at this first stage history H1, doctors will choose one IV fluid level for the patient. So the IV fluid level can be either no fluid, low level, mid level, or high level. So whatever the doctor chooses to do, that has to be one from this set script A that has 4 elements. So that means the first stage treatment is going to be a function that maps the first stage history H1 to this set script A. Okay. So in this way, I can define the consecutive stages. In general, in the stage K, the doctor is going to look at the K stage history HK, and then they are going to make a treatment assignment. So that means the K stage treatment assignment is going to be a function that maps the K stage history HK to some treatment option in this set. Okay. So in this way, I will have total K many treatment assignments. So they are going to be K many functions, and each function is going to be a map from the corresponding history to this set. Oops, I actually didn't realize that some part is getting out of the slides. So this actually says script A here. So if you don't understand some part of the slide, then please ask me. So anyhow, so I have all these K management assignments, and then this policy pi is just going to be a set of all these treatment assignments. Okay. So this is going to be my policy pi. So now I am, okay, so now I'll give an example of a policy to clarify the doubts. So this is an easy example. Suppose in stage 1, I just look at the blood pressure, and if it is below 90, then I go for IV fluid, otherwise I refrain from it. Now suppose in stage K, I look at the blood pressure at this stage, but also at the previous stage. So in this way, I am taking into account the history. And I also look at the lactate level at that stage. So if the blood pressure is low for this stage and the previous stage, and the lactate level in this stage is high, then I go for IV fluid. Otherwise, I do not. So now this is a very simple example, and I can make the dependency on the history much more involved. But the idea behind this policy was just to give you a simple example so that the ideas are much easier to understand. I am now ready to define the optimal policy, but if you have any question about the setup that I described till now, it will be a good time to ask. Okay. Yeah.
So the policy is essentially some sort of tree.
Yeah, so that's a good question. So let's go back. One thing I forgot to mention is maybe those people who are already familiar with reinforcement learning, they might have some confusion, because in our case, policy is not one function. So policy is going to be a combination of K many functions, and each function is going to be like a map from the history to the set of treatments. So in traditional reinforcement learning, I don't know if you are kind of coming from that background. Okay, so what happens is that in reinforcement learning, policy just means one function because they have the homogeneity. So if you have the homogeneity assumption, then every stage is same. So you don't have to have K different type of assignments or K different type of smaller policies. You can just work with one single policy. But since in my world, like all the stages can be very different from each other, so I have to consider different type of treatment assignments or different type of small policies for each stage. And then my final policy is going to be the combination of all that policy.
Like structurally, each individual function that acts like a tree, or how are you?
Yeah, they can act like a tree, or they can be linear policies, or you can also use neural networks. So they can be anything. They just have to be some function on the edge, and now they can be anything.
Okay.
Yes.
It's a recursive structure. Why use the offline learning setting, not the online learning setting? What restrict your setting to be offline? Why?
So the answer is that, okay, like technically there is nothing that would stop us from making this an online setting. But in the medical case, suppose I am learning a policy and then I want to evaluate it on the patients, and I just can't go to a hospital and do that. So when I talk about the word optimal, I need to define an objective function first, because without a clearly defined objective function, the word optimality does not make any sense. So to do that, I will be using language of causal inference, and I will denote by potential outcome, YK pi. The potential outcome at stage K had policy pi been followed. So this basically means, suppose you are in a world where this policy pi was the observed policy. So that means, suppose you are in a world where doctor was using this policy pi, then the outcomes that you will observe in your data in that world, so they are going to be the potential outcomes. Okay. See. Our objective function, the value function, is nothing but the expected sum of these potential outcomes. And the policy, optimal policy pi star, is going to be the maximizer of the value function. And the goal of this talk is to estimate this policy pi star. Now I want you to consider one thing. So this expression of value function seems pretty straightforward. So it's just a sum. But you have to keep in mind that these values, the potential outcomes, are not something that I have observed. Okay, because in my world, Dr. May have not used this policy pi. So I do not exactly observe these outcomes. So when I want to estimate the sum of their expectation, it's not going to be very straightforward. But there are some causal identifiability assumptions. Under those causal identifiability assumptions, you can write this value function as an expectation of observed random variables, and you can estimate that. And then you can use it later in this maximization step. So I am not getting into the details of the causal identifiability assumptions in this talk, but if you are interested, we can talk about it after this talk is over. Okay.
Is the expectation the pure expectation or conditional expectation?
This pure expectation, no conditional there. Okay. Now I am going to discuss some existing approaches of estimating the optimal policy. And although I am not clearly stating it in this slide, the causal identifiability assumptions I was talking about, they are there. So without those causal identifiability assumptions, we cannot estimate the optimal policy because we cannot even estimate this value function. Now, there are two mainstream approaches of estimating the optimal policy pi star. So the first approach is called the dynamic programming approach. And the second approach, I'll talk about it. It's called direct policy search. So what does dynamic programming do? So under those assumptions, we actually have a formula for this pi star. So once you have a formula, now you can model different parts of that formula to estimate that pi star, right? So that's what dynamic programming does. So methods like Q-learning and L-learning, so they use models which can be either parametric or non-parametric to model the formula of pi star. Now, the problem with the parametric methods is that they face model misspecification. Misspecification is quite an issue because we have this longitudinal setting here. And for non-parametric methods, you generally require a large sample size for non-parametric model to perform well. But in my experience, when you have large sample size, methods like deep Q-learning that use deep learning or like say neural networks for modeling part, they perform quite well. Now, there is another recent approach that's called direct search or direct policy search. So the idea behind the direct policy search is that I am not interested in the data generating mechanism. I am just interested in this pi star. Now, if to estimate this pi star, which can be represented as the maximizer of this value function, I need to go through all this modeling. I might be doing some unnecessary work, especially because in this longitudinal setup, modeling is quite difficult. I can have high dimensional data and I have so many stages. Modeling is not an easy business. So if that is not required, then can't we just maximize the value function and estimate what is the optimal policy? So the obvious advantage is that it can be relatively model free. But the problem is this maximization is generally not going to be very trivial. And directly carrying out that maximization is difficult. It is computationally infeasible for a number of reasons. So what people do is they reduce that original maximization problem into some more manageable machine learning problems, and then they solve those machine learning problems. And this type of reductions currently are available only when we have two treatment options at each stage. So remember that the example I started with, I have 4 levels of treatment. So I have no IV fluid, low, medium, and high level of IV fluid. So I cannot use the existing methods in direct search to apply on my example. So the goal of this project is to lay out a framework for direct search for arbitrary number of treatments. And remember, I need to give one method of solving that optimization problem by reduction to easier machine learning problem or whatever that need to be computationally efficient. And also they need to scale to the large sample size of electronic health record data. So this type of data I will get from hospitals, they will generally have large sample size. So whatever I end up doing, that needs to scale to that sample size. Okay. So now I'll introduce the proposed method. First, I am going to talk a bit about the true treatment option. Like what is so special about this option so that it's easier. Like we have methods for direct policy search in this case. So my plan is that I am going to look at this from a high level. I will not go into much depth, but I just want to give you the idea and intuition behind what's happening. So consider I have a septic patient. I have stage 1, so I only see first stage history. When I have only true treatment, then I can consider there is just 2 options. I either give them IV fluid or I do not give them any IV fluid. Okay. So now consider this patient population. So I can think that they belong to 2 classes. So the red class, these are the people who benefit from the treatment in the first stage. So that means if I give them the treatment in the first stage, the outcome will be better than the case when I don't give the treatment. And the blue class is those people who don't benefit from the treatment. So in those cases, if I give them the treatment, then the first stage outcome will be lower. Because remember, in our case, outcome meant higher values of outcomes are preferable. So if I knew the class membership of each patient, then I could just use that information to assign the treatment. Because if I knew that a patient belongs to the blue group, then I would know that they don't benefit from the treatment, so I don't give them the treatment. And actually, it can be shown that if I knew the actual class membership and I was giving treatment accordingly, that would actually be the optimal treatment assignment. So that aligns with the optimal treatment assignment. So that means, yes.
Sorry, I think it's so complicated. My head is sweating.
Oh, no worries.
So, when the medical is signing the treatment,
Yes.
Is it possible that 2 patients with the same set of covariates will be assigned different treatments?
Okay, so that can happen if they say they lie in the decision boundary. Okay, so let me.
Are the medics working according to a protocol, or are they not?
So the medics will not. So that cannot happen in the real situation. So the medics generally have like a fixed policy. So they will not give the. So there cannot have arise a situation where for each patient, they will be kind of split between I can give treatment or not give treatment. So each patient, they will receive either treatment or not receive treatment.
Okay, so the same patient, say 2 patients with the same behavior will get essentially the same treatment.
Exactly, yeah. And also when you talk about like the same behavior, like that is being captured by like the covariates or history. So what you are saying is basically if they have similar set of covariates, they are going to receive the same treatments. Okay. So here what I see is if I, okay, so then the fastest treatment assignment problem, it reduces to a binary classification problem. So I am not getting into details of the binary classification, but one thing I want to mention is the first stage outcome that I observe in the data is going to play a role in this binary classification. And actually that works as an weight in this. So this is not going to be just a binary classification, but a weighted classification. And the outcome is going, yeah, the first stage outcome, the first stage reward will drive this classification. But this is the idea. Any question? Yes, go ahead.
I'm just assuming that no benefit from the treatment. Are we considering that there is some kind of threshold? So if someone is going beyond that threshold, we are saying that the treatment is working for that patient, or then it's below that, we are saying it's not working for that patient. So if that's the case, then why we are just interested in 2 clusters? If it's based on some threshold or some kind of thing, why not just create like more than 2 clusters to accommodate like different low, medium, high levels of treatment?
Okay, so the first thing is that this is actually not based on like a threshold. So when I say they are not benefiting from the treatment, that means that It's the expectation of the outcome when you give the treatment is lower than the expectation of the outcome when you don't give the treatment. So you are looking at the expectation of the outcome. So it's like the outcomes, they inform you whether the patient benefit from the treatment or not. And also another thing is what you just propose. So that is exactly what we will be doing when we have like more than 2 treatments. So in the next slide, when I start talking about more than 2 treatment options, you will see that what you are referring to, probably that's what I think, like what you are referring to, that I can separate them in more clusters. That's what is gonna happen. Okay. So is any question? Any more questions? So thank you. Yeah.
The pipe taking two values, 0 and 1 in this case, right?
Exactly, like -1 or 1 or 0, yeah, whatever. So thank you so much for those clarifying questions. So now I'll move on to the case when there are more than 2 treatment options. So I have low, medium, high, and no treatment. And so in this case, I can divide the patient population in 4 categories. So the green category is those patients who respond the best to low level of IV fluid. And what do I mean by the low level, like they respond best? So that will actually mean that the outcome will be the largest, or the expected outcome for the patients with those type of covariates will be largest when you give them the low level of IV fluid. The orange one will be those patients who respond the best to the medium level of IV fluid, and then I can define the 4 categories in this way. So then if I knew the class membership of this patient, then I would know which treatment they will respond the best to. And that would be my treatment assignment in the first stage, right? If I knew that class membership, then I would, so I knew, suppose that the treatment I am looking at, they were in the blue class. So that means they respond the best to, sorry, there should be a space, like no treatment. So they belong to this class. So for that patient, I'll not give them any treatment. So then even if I have more than 2 treatments, then treatment assignment at this stage is like a classification with more than 2 categories. Okay. And when I have a classification problem with more than 2 categories, then I will call that a multi-category classification problem. So I am illustrating all this with just a first stage for the sake of simplicity, but actually you can show that for any stage, things like this are going to happen. And in any stage, the treatment assignment reduces to a multi-category classification. Okay. So then that gives us an proposed algorithm for this whole problem. So I start with my patients, and then for each stage, for all these case stage, I have many multi-category classifications. And but the subtle thing here is that these multi-category classifications are not all independent. They are all connected at the end by this loss function. Okay. So that means I cannot solve this multi-category classification separately using off-the-shelf methods. Okay. So one thing about this loss function, so I am not getting into the form of the loss function because it's a little bit convoluted, but it's basically based on a smoothed out version of our value function. And also it is going to be non-concave. Since it is non-concave, no matter what you use for the multi-category classification, like someone is talking about tree, say I use my tree-based policies, or like whatever you use, even if you use the simplest linear policies, whatever you use, you will always end up with a program that is necessarily non-concave. Okay. And also I am using the word optimization because this whole program, this whole algorithm is actually a layered optimization problem at the end, where this is the loss function. So that is what it will look like. Now okay, so I already told that this is non-concave, but it is smooth. You can ask me that, can't I just do convex relaxation of this whole optimization? Why that will not work? So in my previous paper, I have shown that if you use convex relaxation, then you are most probably going to run into like the ultimate solution that you get that will necessarily be suboptimal. So you cannot solve this problem via convex optimization. So that can be rigorously proved for this particular problem. And this actually also happens in some hard machine learning problems like ranking. You cannot solve them by convex relaxation. Okay. Fine. So now the final solution is going to be pi star if I use this particular loss function, but it's a population level solution. So population level solution means that, oh yes, so now I have the things. So the population level solution means if I had infinite number of data and I applied my algorithm, then I would get the true optimal policy. But since in practice, I don't have infinite number of data, what I get is an consistent estimate of this pi star. So the policy that this program is going to output is going to be a consistent estimator of this pi star. Okay. So another thing I want to mention is that I can use stochastic gradient descent because this at the end gives me a smooth optimization problem. And stochastic gradient descent actually works on this program. So the benefit of stochastic gradient descent, like those of you who don't know about that, is when you have large sample size, stochastic gradient descent makes it manageable. So our method, it scales to large sample size of electronic health records because we can use SGT. Okay. Okay, so I don't have much time and I actually want to discuss about the open problem. So I will just go to an example of the toy data, like how this is performing on a simulated data set. So this work was done by Sneha, who worked with me in the summer. She worked very hard and she implemented this method. So for this toy data set, I have just 2 stages. The number of treatment at each stage was 3. So this was basically the diagram. And I used a neural network for the classification. So that also means that the policy you will get at the end of the day, they are also neural network. I am not getting into the details of how I do the classification because I'll not have the time here. And I used just 3 covariates and everything was Gaussian and the rewards were being generated by a linear model. So this was like a very simple case, just linear models and Gaussian data. I am comparing our method with Q-learning. So Q-learning is the gold standard for this type of problems. So what I am plotting here, I am plotting the sample size. I have quite large samples like 10,000 data. And then I am plotting the value function. So generally to compare two policies in DTR, we look at the value function. Why? Because remember the value function was the sum of total reward. So if one policy has better value function than the other policy, B say, that means the first policy generated higher total sum of rewards. So the rewards were on average higher for the first policy. So that's why I will say the first policy is better. We see that our method, the blue one, that has higher value than the Q-learning. And also for our policy, the difference between Q-learning and like our method that slightly increases as the sample size increases. I will go to the open questions now, but if there are any question or like any doubt you want to clarify, I can answer them. Yes.
I guess I have a question, maybe it's part of the questions, but how are deaths coded in this data? Because especially for sepsis, I guess that's a motivating example. 30% of people will die if they.
I'm sorry, so what is the how are what?
How are deaths?
Deaths.
Patients.
Oh, okay.
People dying coded within, for instance, the sepsis data.
Okay, so we are not currently considering survival outcomes, like say when you consider death. So for now, what we are considering, like the outcome is basically the lactate level. But what you are saying, if you want to code death, then you just look at one outcome at the end. So your YK is going to be 1 if they say survive, and your YK is going to be 0 if they die. and you just don't consider like the outcomes in the previous stages. So because we are ultimately interested in the date. So in your case, like y1, y2, they are all going to be 0 up to yk minus 1. And so that is going to be 0 for everyone, like every policy, everything. And finally, yk is going to be 1 if they survived and not. So in this way, you can make this a survival.
I guess I mean more from the survivorship bias perspective of just tracking the lactic acid levels, because in the data set they use, in order to reach K stages, the patient has to be alive throughout all those stages.
Yes.
And so if you're only focusing on patients who have K observations, then you're excluding patients who might have died before they reach the K stages. And like
Yes.
30% of patients reach that death stage.
Yes.
Or maybe some lower number. How does that influence your ability to?
Yeah, sure. So that's a great question, and so that's like an active area of current research. So instead of having all the patients have the same number of stages, you make the number of stages flexible. And so like that can be on their discharge or mortality. So that will be a more complicated set, like a question where the stage is not set, and that has to build up on like the strategy when we just have the same number of stage from everyone. But in the previous papers, what we did, so the number of stages, they are not like very large, say like 100 or 1,000. So in this particular problem, they are generally going to be small, like say 10 or so. And you look at like say patients who just survived for the 10 hours since the admission to ICU. Okay. But the ultimate goal is to go where you are considering, like where you can make the whole thing more flexible, and there are many room for adding flexibility. Like you can also ask the patients might not get treatment at the same time, so how you are synchronizing all these patients. So all those real considerations are there, and all these are active area of research. Okay.
My question
Yes.
is still on the optimization part. So there are key treatment, capital K. And but I cannot see for example, the first treatment is after a year, the second treatment is just a week. Like the time dependence between each treatment, this kind of consideration.
Sorry, can you repeat your question?
So in the optimization part,
Yeah.
it's optimized over the key treatments. Right, but for example, the first
Yeah,
treatment happened after 1 year. The second treatment happened only after a week. There should be some time dependence, right?
Okay, so because we are looking at observed data, and also here like the stage difference, like the time difference was like an hour, like we are not looking here or but whatever. So since we are using observed data, like we are getting into the analysis after we have observed everything. So even if it led to 10 years, the data you have, like those things are already there. Yeah, maybe we can discuss more about this offline. So the first offline question is about the implementation and the optimization part. So I just showed you a very toy and simple example, but I didn't get into the details of the implementation. So this is basically what the implementation will look like when you have K stages and 4 treatments per stage. Please forgive me because I am showing you this picture of the implementation without analyzing how we come to here from there. But just let me tell what is the problem. So what you'll need to do, so in this case, suppose I am using the neural network classifier, so I am using deep learning to solve those classification. Then for K stages and 4 treatments, so you can see K blocks here. So each of these block correspond to one of those multi-category classification. I have K parallel multi-category classification. That's why I have K parallel blocks. These blocks are all connected by this pink loss. And that is because my multi-category classifications were all connected by this loss at the end. Now at each block, I have these 3 many neural networks. So 3 comes from 4 treatments. So if I have, say, n many treatments, then the number of neural networks I'll have in the stage is n minus 1. So it is always minus 1. Okay, because that, okay, I can discuss that later. So that means if in this setting, if I have case stage and 4 treatment, then I have to train all those parallel neural networks. Parallel means they don't share weights. They are only connected via the loss. Okay. Now, jointly training 3K many networks can be computationally expensive first. And second, it can be difficult for the tuning procedure. So like when K is large, training 3K many networks parallelly can be difficult. But Q-learning, that needs to train only K networks, but what's important is Q-learning trains them sequentially. Now, sequentially training the networks are much easier. So you don't need to tune them, or you don't need to run the optimization problem like the end optimization of the neural network on all these parameters. Okay, so the sequential procedure is much better from stability and computational purpose. So my question is it possible to sequentialize this whole procedure? What I mean by that is, can I train the network sequentially, but I can still have a good approximation of the optimal policy? Of course, like when I sequentialize this problem, maybe the end result, the end policy will change. But what I want is they are not being so bad. I still get a high quality policy as the original joint program is doing, but I have better computational performance. Now, why I think that is possible? Because this thing, like I need like the problem naturally translate to training a lot of neural networks jointly. That is not something particular to this problem. This arises in other domains. Say, for example, in spatiotemporal processes as well. Sometimes you'll see that in some problems we need to train a lot of neural networks jointly. But what they do is they will tweak the original problem and they'll sequentialize the problem so that you can rewrite this problem as a sequence of neural networks that need to be trained. And in my problem, I don't expect that you can sequentialize like the whole thing, but at least if it is possible to sequentialize the blocks, so that means if instead of running these multi-category classifications jointly, if you run them sequentially, then that would be good. Okay, so that was one part of the implementations, but another important thing is the optimization. So we have a non-convex problem. So optimization is a optimization can be a non-trivial issue. And for optimization, currently we are using stochastic gradient descent, but this is like a very general optimization tool. Can we tailor an optimization method for our problem? So that has been done in some other literature. And why I am telling this? Because if you are using neural network, then there are already existing literature that tells you about the optimization landscape. Optimization landscape is nothing but the landscape of the objective function. It will be much clearer when I show you what's happening for linear classifiers. So for linear classifiers, actually, in very simple cases, we can visualize the objective function. And although it's like a very simple toy case, from that we can guess, we can make some guesses what's actually going with the optimization problem. So it's like the very simple trivial case. You just have one stage, you have 3 treatments, and you have one covariate. Then the optimization problem actually becomes like a bivariate optimization problem. And I have drawn the surface. You can see that I don't have local minima or local maxima, although this is an non-convex problem. And actually, like if you draw the whole plot, then you'll be able to see there is no local minima, but you do have flat regions. These are not actually total flat. They have, like, there is non-zero gradient, but the gradient increases very, very slowly. So they appear almost flat. So that means when we are thinking about the optimization of these programs, we need to worry about flat regions. So we need to have those type of tools or those type of say techniques when we are optimizing the neural network that takes care of flat region, but we don't need to worry so much about local minima or local maxima because we will not have that problem. So if we analyze the optimization landscape, then that will better inform us like how should we carry out the implementation so that we have a stable rule. Okay. So if you do this, if you take this question, then you will learn DTR, PyTorch, working with deep neural net, convergence of optimization methods, so some bit about non-convex problem. And the second one is more theoretical in nature, so I'll not get into that. I'll not have the time. Now, another method, so I'll just take 2 more minutes. So another open question that I want to just mention is, in this current method, I am just talking about direct policy search, but I can combine the model-based methods and the direct search to come up with a more robust hybrid method. And actually that is going to work better than the previous method when I do not know what was the actual treatment assignment probabilities. And it is doubly robust. That means it is going to, the estimated policy is going to be consistent if either the model assumptions here or the treatment assignment probabilities are correctly estimated. And if you consider this problem, then you will learn DTR, and this problem depends on Q-learning a lot. And it also borrows a lot of ideas from offline enforcement learning, an area in offline enforcement learning called policy evaluation. So this estimator is actually inspired by that. And also some doubly robust literature in causal inference. So sorry for taking more time, and this is where I would like to stop. And if you have questions, sorry, I rushed at the end, I'll be very happy to take questions now. Yes.
So your case is
Yes, now my case fixed.
I was wondering if this trade off in your problem that you just maximize your V5.
Yes.
So that's why at every stage you are like a greedy algorithm. Like at every stage you are maximizing your V5.
Yeah. So so what do you mean by the trade-off? Like trade-off between whom?
So any problem, there's a trade-off, right? Like let's say like a penalty thing.
Yes.
But here there is no trade-off.
No, so the version I talked about, there is no trade-off, but actually if you have like a large sample, say the covariates, that is like high dimensional, say you have 40 or 50 covariates, say for example in this actual sepsis data, then for real data implementation, you will need to probably use a penalty, like the program that I have shown you, like I have this value function, you can add like an L1 penalty or L2 penalty with that. So if the problem goes high dimensional, then you need to use something like that.
Okay, so if we want to get good UR in smallest possible states,
Yeah.
it can also in smallest possible states. That could also be a trade-off, right?
So you
So,
are,
yes, like our number of states is less than here. We want to minimize that, but also maximize the result.
I see. So what you are saying that you are considering about an trade-off, that you will give treatments like whatever treatment level for say the first few, and then for the rest few you will go for no treatment. So that's what you mean by minimizing stages.
Yes, minimizing stages but maximizing the work. So this is the trade-off.
I see. So the benefit will be the patient, they can be discharged
Yes.
quickly or whatever.
I think that is related to the optimal stocking problem. That the optimize on the stage also.
Right.
Yeah. The market.
I
But
think
the expectation should be the conditional expectation in that sense. First, it's just the pure expectation. It's different.
Also, you could maximize the last reward more, right? If you are putting same weightage for
Yes.
all the rewards, but if I stop it at gate state, so my reward should be better in the end, right?
Yes, so you asked 2 questions, so I will answer to them now. So the first question was, so in your first question, what you are basically trying to say is, I am going to prioritize the no treatment option because it has some more benefits. So I can prioritize the no treatment option when I already have given the treatments for some stages. I think you can do that, and for that you will need to curate the value function. So that's like your optimal, like that is the loss function at the end. You can put some weight so that in the say last 4 stages or after some stages, the no treatment option is going to have more weightage than the other treatments. And what you said, like the final stage, the final treatment. Yeah, so for that, that will be relatively easier to do. So I just took the plain sum. Instead taking the plain sum, you can use whatever you
And that
want.
is like, that can be really done.
That is, yeah, the last thing is can be very trivially done.
If you solve it for the normal average, you can do it for good.
Exactly. So whatever works for like this normal average, that will be done. In reinforcement learning, actually, they will put much more priority to the fast treatment because that's what you just see right now. So there is a discount, but what you are saying is kind of like a reverse discount. So you are going to put more priority to the final stage. But this type of weights, like they can be very easily done.